All right, welcome back. So today we are going to be looking at molecular bonding. So these are obviously, we know our ionic is between metal and nonmetal, so these are going to be between two nonmetals. So we're just going to be looking at a theory that's going to help explain kind of their structure and how they actually form. So one of the major differences right now, we're going to be dealing with something called covalent bonds. So this is just the sharing of electrons. And keyword here is sharing, so it's not a transfer. Is sharing of electrons between two or more nonmetal atoms. So they're going to share so that all atoms achieve a full outer energy level or a full valence, and the sharing of electrons are due to the similar electronegativities that nonmetals have. So just remember, electronegativity is the ability of an atom to attract electrons to itself. Then of course we have our molecular compounds. These are compounds of two or more of, or two of the same. Oh, sorry, I was looking at the element and I was reading it. The molecular compounds are two or more nonmetal atoms bonded together, where molecular elements is two of the same nonmetals bonded together, right? So there's 7 of them in total, which we can use our acronym right here. But remember, if there's just 2 of them, these are called diatomic elements, and if there's more than 2, these are polyatomic elements. So we're going to look at why these bond here anyway. But our main reason is that we're looking at these here is that we know the atomic theory states that the chlorine atom, because chlorine looks like this, it has 7 valence electrons, meaning that it only needs 1 electron right here. So this is the only one that isn't bonded. So it needs 1 more electron to make a stable valence or a stable octet. So this electron can be obtained by sharing an electron with another chlorine atom, and that is why we have something like Cl2. So let's look at that example plus another one. So like I just drew on the other page here, if we have 1 chlorine atom that has 7 electrons in its valence, and we know it exists as Cl2, so we can get another chlorine atom as well that has 7. Now, in our ionic formation, we've seen a transfer, but we can have a sharing of electrons like this. And by circling like this, we're showing that they are shared. So now it's saying that these 2 electrons are shared equally between this chlorine and this chlorine. So when you count how many electrons, remember we need 8 to have a stable valence or a full valence. We have 1, 2, 3, 4, 5, 6. And in here we have 7 and 8. So this chlorine atom technically has 8 electrons. And same with the other one, we have 1, 2, 3, 4, 5, 6. These are shared, so it is 7 and 8. So that is why these configurations happen. Now for our oxygen, so for oxygen, we know this is in group 6A, so it has 6 electrons in its valence. We go 1, 2, 3, 4, 5, and 6. Now we know oxygen is an element, as we can see right here is O2, so it can bond with another oxygen. Now one thing you'll notice is that, well, we have our 2 unpaired electrons, so these 2 can participate in bonding, but we'll notice that these down here are also unpaired and can also participate in bonding. So now we have something unique where we can get oxygen sharing multiple electrons. And that brings us down to our next little topic here, is these multiple bonds. So we're going to classify something as a single bond. It consists of only 1 electron pair. So for example, from our thing right here, this will be classified as a single bond. Whereas a double bond is the sharing of 2 pairs of electrons between the same atoms. So for example, this is our double bond. And we have a triple bond, involves 2 atoms sharing 3 pairs of electrons for a grand total of 6 electrons in total. So no, I don't have a triple bond drawn there, but I will draw this one down here. So down here we have just multiple examples of multiple bonds. So we're going to do water, carbon dioxide, and nitrogen. So for our water molecule, water is H2O. So we have our oxygen, and we know it has 6 valence. So 1, 2, 3, 4, 5, and 6. Now for our hydrogen, it only has one bonding electron. So we can tell for H2O, these are shared, and these are shared. Now, I know what you're probably thinking is when you're looking at it, it's like, oh, there's two here, that's a double bond. No, that is not the case. Because when you look at here, this is just a single bond. And this is also another single bond. So, when you look at the definition of a double bond, it's sharing two pairs of electrons between the same atoms. So you only look at what is happening between two atoms, and that's it. So when you're trying to figure out the bonding between this oxygen and this hydrogen, you only look at this oxygen and this hydrogen. So another way to kind of think about it is that completely cover up this hydrogen right here when you're thinking like just kind of covered up like this, or well, that's not working. There we go, I managed to get it covered up. So you completely cover this up and forget it exists, and you only look at what's happening between this oxygen and this hydrogen, and that is a single bond, right? Now if you want to look at the other one, same thing, you completely cover up what's happening here, and you only look at what's happening between the two atoms. And here we see this between this oxygen and this hydrogen is a single bond. All right? So moving on to carbon dioxide. You know, carbon dioxide is CO2. Now carbon, its valence looks like this. So we have 4. Oxygen we've already done has 6. And the other oxygen. Oops. I'm just going to change that a little bit, and you'll see why now in a sec. So I'm going to double up down here. Now, when we look at pairing these up, obviously we can pair up right here because these are close. But now we'll notice that we can pair up these. Same thing here and here. Now, by taking the same logic we did last time, is that just imagine you only looking at what happened between two atoms. So if I want to figure out what's happening between this oxygen and this carbon, I forget what's going on over here, so I cover this up and I look at what's happening between these two atoms. We can see we have 1, 2 bonds, or 1, 2, 3, 4 electrons. So this right here, that is a double bond. So I can put that in. And likewise, the same thing happens with this carbon and this oxygen. So if you did want to figure out what's going on, you cover up what's happening, and you look here between this carbon and this oxygen, we have 1, 2 bonds, so that is also a double bond. And finally, our nitrogen is our last one. So nitrogen we know is N2. So nitrogen has 5 valence electrons, and the other nitrogen also is going to have 5 valence electrons. Now this is going to be an example of a triple bond because we can tell that we need to have 1, 2, 3 bonds shared in between them. And that is our triple bond. Now, of course, we can, and we're going to get this later, we can use a single line to represent a single covalent bond. So for example, our water, if we want to make this a little neater, we can write H, single line for that single covalent bond, O, and then H. So that will kind of be the same thing. And same thing if it's a double bond, we can get O, double bond C, double bond O, and the triple bond looking like that. So that is possible to change out the single lines with the double lines or triple lines. But that is fine. So we're going to get to that next on the next page anyway. But of course, figuring out like this is a formula for oxygen, carbon dioxide, nitrogen, there are going to be rules to figure out how to do this. So you guys are going to do this on your own as well. So we're going to do something called Lewis formulas. So another way to think of it is kind of electron bookkeeping because we're just counting how many electrons each thing has, whether it's shared. Now, when we're doing this, we're always going to show the electrons are involved in bonding. And that was the whole point of this. So the Lewis formula will aid in predicting the molecule structure, shape, and polarity, which we will get into later in this unit. So let's look at some of the terms first, then rules. So this is just a little note or reminder. Arrows are indicated transfer of electrons. we do this for ionic, and circles are going to be the sharing, our molecular compounds. Okay? Now before we go in, just a few little terms. First, bonding capacity. So this is the maximum number of single covalent bonds that an atom can form, or basically how many bonding electrons there are. And that is what we call the bonding capacity. So nitrogen has 3 bonding electrons, so its bonding capacity will be 3. Now for our terms when we're actually drawing out these molecules, something that's referred to as a central atom. This is the atom that all other atoms are attached to. And it's basically in the middle of our molecule. And the ones on the outside, we're going to call these the peripheral atoms. Just kind of like how you have peripheral vision, it's kind of the outside of your vision. Same thing with atoms. So these are just attached all around the central atom. Now, let's look at our rules for drawing our Lewis structures, and then we'll get into actually drawing them. So, first of all, we need to find the number of bonding electrons in each atom involved. This determines the bonding capacity. And that'll be important because when we go down to step 2, the atom with the highest bonding capacity is the central atom. And we're going to place it right in the middle with the appropriate valence electrons around that central atom. Next, number 3, we're going to arrange other atoms, call these peripheral atoms, around the central atom. Now first, we're going to place the appropriate valence around each peripheral atom, and we're only going to make a single bonding pair first. Alright? Do not try to create double or triple bonds. First, only do a single bonding site, and that's it. Because after we just create the one, this is where we go to step 4. If any bonding electrons remain on any of the atoms, form a double or triple bond to ensure that every atom has all of its bonding electrons bonding. And next, last but not least, we can draw structural diagrams of the molecule by replacing the circles with lines. So for example, on our next page, this is just to give you an example of hydrogen cyanide, right? We can tell we have carbon in the middle, we have hydrogen on the left, nitrogen on the right here. We can tell there's a triple bond right here, and a single bond there. Now, as we can tell, this diagram kind of looks like a little bit of a mess. So we can go from our Lewis dot diagrams, which shows all the dots, circles around it, to our structural diagram where we replace the single bond with a single line and the triple bond with 3 lines. And we still write in our lone pairs off on the side there. Now, sometimes as well with bigger molecules that we're going to get into, chemical formulas are often written in ways that provide some hints about their structure. So we got C2H6O. So if we did out, we followed our rules. We know carbon has a bonding capacity of 1, 2, 3, 4. Hydrogen has a bonding capacity of 1. Oxygen has a bonding capacity of 2. Right? So we know that carbon should be my central atom. And for the most part, you kind of want to place it there. But notice here how we have C2 in this one right here. So the fact that we have this chemical formula is telling us that 2 carbons are together, that's telling us that we need to have these carbons as the central atom. Alright? Because if you look at the dimethyl ether example over here, we see carbon here and carbon here. So they separate it, and that is for a reason. So over here, where it starts off with C2, I know these carbons are my 2 central atoms. Now, so I put them in and create one single bond. Next, if you look at it, now normally you want to go, like there's nothing about, you attach your second one or whatever, but notice how we have H5 and then OH. So the fact that this hydrogen is here and not piled up here in the middle tells me that they want to have oxygen and hydrogen bonded together, but also we need 5 hydrogens bonded around as well. So just because that, I'm actually going to go here and start bonding a bunch of hydrogens together to our carbons. Now, I'm not going to load all of them up on one carbon. I'm going to go back and forth. 1 hydrogen here, 1 hydrogen here, 1 hydrogen here, 1 hydrogen here, and 1 hydrogen here. Now that's our C2H5. Now notice how we have OH on the side, so I'm going to put in my oxygen next, because that's the next one listed, and then our last bonding electron here, we have our OH. Or we can make it structural diagram like this if you want to make it a little neater. So you'll notice that the reason they've written it like this is because they want to have this hydrogen attached to this oxygen right here, so we actually see it right here and we have 2 carbons as our central. Now for our dimethyl ether, notice how we don't have the same chemical formula. We see CH3OCH3. So this is giving you a hint that it wants you to start with carbon and that oxygen should be in the middle. So that means, starting with carbon, we have C. Then we go H3. Then we go O. Then C, H3. Right? So same thing. If I just want to make it a little neater, I can as well. So these are the same thing, but just notice on how I drew these out, right? Once again, we have a little idea on how they should look based on their chemical formula. C2H5OH, C2H5OH, right? CH3OCH3. These giving you little hints on how you need to draw them. So always look at the chemical formula when you draw them. Your chemical, how your chemical looks should almost represent how it is in the formula as well. And that's just kind of a little hack that we're going to get into, especially when we get into larger molecules or when you do Chem 30 with organic. All right? Now, these here obviously are going to take a little more practice, but most of the practice we have right now is going to be for the smaller ones because we're going to get into the bigger ones later. So right now, I want you guys to work on these here. So how this works, we have bonding capacity, Lewis structure, and structural. So first, for every single one, you should definitely write out the chemical formula somewhere to give yourself an idea. So like boron tribromide, we know that's Br3. So our atoms are boron and bromine. So boron and bromine. Now I am going to write out their Lewis formulas, right? So periodic table, we see boron here. It's in group 3A, so that means it has 3 electrons. 1, 2, 3. Bromine is in group 7A. It has 7 electrons. Now for the bonding capacity, right, you only look at the number of bonding electrons. So for boron, we see 1, 2, 3 bonding electrons. Bromine has only 1. Remember, these are lone pairs or non-bonding electrons. So we have 1 compared to 3. So that means my central atom is boron. So when I'm following the rules, I write the central atom in the middle and then write its Lewis dot formula. Next, I'm going to place my peripheral atoms, which must be bromine, around. So from the chemical formula, I need 3 bromines. So I'm going to create 1 bromine, bond it, write out its Lewis. Stick on another bromine, bond it, write out its Lewis, and then finally the last bromine, bond it, and finish off with its Lewis. Now we'll notice that there's no more bonding electrons. All right, everything is full. So we don't need to add any double or triple bonds. We can just write now our structural formula, replace the circles with lines. Sorry, it's a little tight right there. And boom, we have that done. So that's how you're going to go through all these here. All right, so you can do it for ammonia, hydrogen peroxide. Just remember this is a hydrogen-containing compound, so there's a little trick to that. Review your Chem 20 notes. Sorry, not Chem 20, your Science 10 review notes on naming hydrogen compounds. It should be around the acid section, and you'll get that. So you have hydrogen sulfide, same thing, chloroethane, and when you go through, you got ethyne, methylamine, methanoic acid, and methanol. So you'll notice I gave you the chemical formulas for every single one because I don't expect you to know that this is methylamine. All right? So practice those. When you get them done, open up Google Classroom, check the notes to make sure that you have everything filled in correctly, and put a check mark by it if you got it. If it's wrong, mark a little X, figure out where you went wrong, and try it again. All right? And then, of course, you can try your CYU book with the corresponding stuff here. Now, this is end of our stuff before our first quiz. So if you're watching this because you're in isolation or you're sick or whatever, whenever you come back to class, there will be a quiz on the last 3 sections that we touched up on. So formation of molecular compounds, ionic compounds, and of course our introduction. All right? So see you guys later when we'll be looking at molecular shapes and dipoles.